So, today I will start with the Acousto-optic shutter and I will speak about the saturable absorber and how short are the short pulses. That is what I am going to describe, because in the last lecture I think I stopped at electro-optic switch. I described the electro-optic switch in a bit of detail, and the Acousto-optic shutter I will describe today, the concept, in a little bit more detail, and the saturable absorber too. So, so these are the three shutters that can be put in a resonator, can be put in a resonator in order to get Q switched pulses, okay, or even mode locked pulses. So, we started off with Q switch and I gave you these three shutters. So, here let me describe the Acousto-optic shutter, which is a material, as you can see here, consider it to be a material which is here. Okay, it could be a crystal, it could be a semiconductor part or anything. Assume it is some kind of a crystal or glass, to which is attached a piezoelectric transducer. You know. So, to this piezoelectric transducer you apply a voltage and the piezoelectric starts vibrating. That is what is piezoelectric. It starts vibrating and that sound vibrations move into this material also. Okay. So, this Acousto-optic absorber, you know, it absorbs all this acoustics that has been generated from the piezoelectric transducer, and what it does is it forms alternate regions of rarefaction and compression, rarefaction, compression, rarefaction, compression. It forms this in your physically in that structure. So, where you have compression, there is a larger refractive index, and where you have rarefaction, there is a smaller refractive index, and so this smaller and larger refractive index, they alternate. Okay. So, since they alternate, they actually look like a grating. You know, it's sort of a kind of a grating, acoustic grating. So, when the pulse is on, or when your piezoelectric transducer is on, then you get this grating. So, when you have a light input beam which is coming here, it faces a grating. So, what does a grating do? It just deflects off the light, depending on the wavelength or whatever, it deflects off the light, that you know in any kind of grating. Okay. So, this is what happens to the beam. So, you put on an alternating voltage or a direct voltage, whatever, to make the piezoelectric transducer work. The moment the piezoelectric transducer is working, your input beam that is coming in, it gets deflected off. Okay. And here what this transducer is placed within your resonator. So, suppose this is the resonator and your shutter is here, as shown before in the previous slide. So, your light is coming in here and it is getting deflected off, and it gets deflected off and does not reach this rear mirror, this mirror here. Okay. It does not reach that. So, obviously, nothing is reflected back into the cavity. Okay. That means when you are putting on the transducer, the shutter is closed as far as the light beam is concerned. Okay. The moment you remove the piezoelectric transducer, your grating style disappears, and the moment grating style disappears, the beam just goes through, passes through. It is transparent to this frequency, it passes through and reaches this mirror. Okay. So, here it goes here, this is your shutter, and okay, now this has become transparent, it goes here and it reflects back and goes into the medium again. And again again when you put, it's at your will. It depends on for how long you want to keep it on or how long you don't want to. So you can keep it on for the time when your active medium population inversion is building up. Okay, you keep it on and then you put it off, and the active medium population inversion falls down and you get a large lased pulse. Okay. So this is how the principle of the acousto-optic shutter. Now let me give you the principle of the saturable absorber. Okay. Saturable absorbers are generally dyes which are soluble in some kind of liquid, can be alcohol or any kind of liquid which dissolves these specific dyes, and or it could be a semiconductor, a CSAM. CSAM stands for semiconductor saturable absorber and M stands for the mirror. So it is a saturable absorber. Now how does a saturable absorber work? By the way, the saturable absorber is called a passive switch or a passive shutter, and the acousto-optic shutter and the electro-optic shutter is called the active shutter. It is active because in case of saturable absorber there is no electric field applied or no pulse applied, no electrical stimulation applied, okay? Nothing of that sort, which is true for the EOS and the AOS. So then how does the saturable absorber work like a shutter? So if you can see this diagram, this is a graph, this is the intensity of your beam that is coming in, your laser beam, okay, and this is the absorption profile of the shutter. The absorption of the saturable absorber is dependent on the intensity. How? At low intensities there is a large absorption, so it goes here. Everything is absorbed and then you are in a saturation state. Okay. The moment the intensity is high, nothing more is getting absorbed, and the absorption is actually coming down and the intensity is allowed to go through, the light is allowed to go through. So you have two states. It's almost like a step function. Okay. It's either in this state or in this state. Okay. So that's the switch. It switches from this top state to this state, okay, depending on the intensity. So it's acting like a switch. It switches from here to here. Suppose this is 1 and this is 0. Okay. It's not exactly 1 and 0 because it's a real system and the fall is not a sharp fall. But in any case, this acts like a switch. So here I have another switch, a saturable absorber. So now I'll describe the saturable absorber a little bit more in detail when I discuss mode locking systems. That's because these passive mode lockers or the passive switches are used more in mode locking, while the active shutters are used more for Q switching. Okay. So before I come to that, let me just give you a comparison of the short pulses that we are talking about. So in this first table here, I just give you some examples of lasers, and they are real systems, and these energies and the pulse duration and everything, they are all experimental values. So I have a ruby laser, Nd:YAG, CO2 and a titanium sapphire, and each of them has these pulse energies, and then you have the pulse durations. Okay. So the pulse duration in case of a ruby laser is 2 milliseconds. In case of Nd:YAG is 100 microseconds, which is little less than ruby. Carbon dioxide laser you can get around 500 microseconds for a Q switch pulse. On an average, these are things, I mean, there can be pulses which are shorter or longer, but in this range, in this scale. Okay. In titanium sapphire you can get even shorter pulse widths of Q switch pulse, 10 microseconds, but they are all say in the microsecond range. And the energy from the carbon dioxide laser is 10 joules, which can be extracted out easily. In case of ruby, in this particular laser, 100 joules has been extracted out. In Nd:YAG, around 500 millijoules have come out. In titanium sapphire, around just 5 millijoules. Okay. So, what happens is then I have to find out what is the peak power here. Peak power. This is all not for Q switched. Sorry if I have said Q switched here. This is all for a free running laser where the pumping system is pulsed. This table corresponds to the Q switch. So, these are all the energies and the pulse durations that you can get. So, what will be the peak power in each of these cases? As you remember, peak power is energy by time. Okay. So, all I have to do is divide this energy 500 millijoule by 100 microseconds. So, I get a 5 kilowatt power, 5 kilowatt peak power. Then you say for example 5 millijoules divide by 10 microseconds. So, here you get 0.5 kilowatt power, okay, a little less than this, but in the kilowatt range, no doubt. In case of carbon dioxide, 10 joules and 500 microseconds. So, you get around 0.02 megawatts, means around 20 kilowatt. So, you get peak powers in the range of kilowatts. Okay. So, this was the free running type laser. Okay. Now, just compare it with a Q switched laser. In case of a Q switched laser, you are able to get much shorter pulses, and you are also able to extract a little bit more energy than in case of a free running laser. Okay. So, here again suppose you compare ruby and diag, CO2 and titanium sapphire. Here I have got 500 millijoules and this is 50 nanoseconds. Here in case of ruby I had got around 2 milliseconds, here it's become 50 nanoseconds, so much shorter. So much shorter, though the energy extracted is 500 millijoules, which is much less than here, still your peak power has become 10 megawatts. So, in case of carbon dioxide, I get 100 joule, 500 nanosecond. Here again the pulse duration has reduced as compared to this, okay, and you get 200 megawatts. So, you see a pulse duration which is shorter, it adds a lot to the peak power here. Okay. So, it is kind of a play between energy and T. You increase the energy or reduce the T. You keep the energy constant, reduce the T, you will still get a large peak power. You can't do much about the T suppose in some system, but you are able to increase the energy, you will still get a high peak power. Okay. So, here my pulse durations have reduced in case of Q switched, and my peak powers have gone into the megawatt range. Here it was in the kilowatt range. So, that is the advantage of having a short pulse. You get very high peak power, and the whole world is just crazy about getting more energy, a higher peak power, a shorter pulse, and the endeavor just goes on and on until in 2023 the Nobel Prize, as I have said before, went to the person who invented the attosecond laser. They went on to shorter and shorter pulses. You just keep on trying to get shorter and shorter pulses, and they found a method of making attosecond. Attosecond means 10 to the power minus 18 seconds. Okay. Femtosecond is 15, attosecond is 10 to the power minus 18 seconds. Okay. So, this is atto. So, this quest for shorter and shorter pulses led to the Nobel Prize for attosecond pulses in 2023. Okay. Then, so in now I have described the Q switched pulse, but suppose I want to go in for a shorter pulse. Okay. So, my only option now is to go in for mode locking. So, let us see what are the concepts of mode locking. Okay. So, you already know that any resonator cavity has a whole lot of modes here, the ones shown in yellow, which which are there in the resonator cavity, and they are all equidistant. I have called it as delta nu, that means the separation in frequency. Delta nu here is C by 2d. D is the length of the resonator, the total, 2d is the the round trip time, and C is the velocity of light. To be exact, you can say delta nu is equal to C upon 2 n0d. N0 is a refractive index. For many practical purposes, you can have it as 1. So, delta nu is C by 2d. So, it depends on the length of your resonator cavity. Okay. So, d is a resonator length. So, but then all these modes which are possible in that resonator cavity, all shown in yellow here, are all equidistant in frequency. See, in frequency, this is the frequency line, they are all well equidistant. Now, but many of these modes may not fall within the gain curve. Okay. So, in my y axis I have written the gain of the active medium. So, the gain follows this blue line curve here. Okay. It has this bandwidth, this much is the bandwidth. So, it is this large. So, only those modes will be accommodated, or only those modes will laze, those which fall within this bandwidth of the gain medium. Okay. So, they have to extract from that medium, from that gain, these modes. So, you can see here 1, 2, 3, 4, maybe about 5 or 6 fall within the gain curve. So, all these 6 modes are supposed to laze, should be able to laze within in your resonator cavity. But then another thing is they have to cross the threshold or the loss line. The green one is the threshold or the loss line. That means many of those modes will suffer losses inside your active medium or within the resonator, going to the walls or getting lost at the mirrors or in many other, or getting absorbed in some way. So, those will never grow. So, the ones which are above this threshold will grow. So, then the number of modes possible in this from the total number of modes is 1, 2, 3, 4, as you can see in this picture. Okay. So, these fall within the gain curve as well as are above the threshold. So, these two conditions have to be met for which modes are going to laze. For an example, let me take an example like this. Here I have taken an example here. I have 50 centimeter long laser cavity. That means D is equal to 50 centimeter. N0 you just assume it is 1, I assume it is 1. Then the mode spacing will be 300 megahertz. That means from here, from this formula you get this 300 megahertz. That between one mode and the next there is 300 megahertz spacing. Suppose delta Vg is the bandwidth of the gain curve. Okay. So, bandwidth means this part, this gain curve, bandwidth, the total bandwidth. So, delta Vg, I have called it G because it is a gain bandwidth. So, suppose that is 1500 megahertz. Okay. Then how many modes can laze? 1500 divided by 300. Okay. Then there are about 5 modes that can extract energy from this gain medium. 5 modes are there. Okay. So, all these can do it. Now let us see how we can manipulate these modes. It is quite easy to manipulate all these modes. In some spectroscopic studies, you require a single longitudinal mode. You do not need all of them because they need one very precise single frequency. Perhaps they are not too bothered about, in those experiments, too bothered about the energy that is extracted. Energy can be low, but my need is to have a single longitudinal mode. So, from all these modes, how do I select only one? So, I do not want all of them, I just want one, the one in the center, say. Okay. How can I get that? So, I have to see to it that these other frequencies here and here on either side, their loss is very high. So, how do I ensure that loss? that these lose out and only this one grows and grows. Okay, this single longitudinal mode just grows. How do I manage that? A very simple method would be if you just look at this formula. Say take a case of a helium neon laser. From this formula only this can be derived. C by 2D N0 is equal to delta Vg. Okay. C by 2 N0 Vg is equal to delta Vg. Okay. Here. This is the condition for a single longitudinal mode laser. So, from this, it is all derived from here. It is very simple. You find D, you know C, you know N0, you know 2 is already there, you know Vg, you know the bandwidth of this medium of the helium neon, say it is 1500 only megahertz. I have just taken an example of the helium neon laser, you can take any other example. When you substitute those values here, what will be the value of D? D turns out to be 10 centimeters. Just put in all those things and you will find it D equal to 10 centimeters for a helium neon, okay, for a helium neon laser. 10 centimeters is too small active medium. Imagine it is just this much length of the active medium. I mean, it seems very impractical. So, what we have basically done here is, how did we wanted to eliminate all these modes. So, we did that by reducing the length of the cavity. So, here we had started off say with 50 centimeters and we had got 5 modes, but here now we only want one mode. We want one mode and the cavity length turns out to be 10 centimeter. So, what have I done here? So, if I draw this gain curve again, something like this. So, I have this one mode which is here and all other modes are falling away from the gain curve. Okay, there may be one mode here. So, I have increased this distance of frequency so that it does not fall within the gain curve at all. And how have I done it? I have done it by reducing the cavity length. Okay. If I increase the cavity length, the number of modes coming in will be more and more and more, much more than this. Okay, this is just a representation. So, what I have done by this is I have just done this. So, this is out of the gain curve. So, this can never laze. So, this is the only one which can laze. So, since this is the only frequency which can laze, which is shown here, okay, a single frequency, single longitudinal mode pulse is here, and this is a frequency, and here is my gain curve. So, what does the single longitudinal mode do? It creates a hole in the gain profile. You can see this hole in the gain profile. Okay. It is fine by me because I need a single longitudinal mode and I have achieved it. Okay. I do not know if I have achieved it, conceptually I have, but then as I say 10 centimeter is kind of an impractical length for a gain medium. So, it may not happen. So, you have to think of some other method of doing it. So, what is the other method? Another method could be, okay, all these frequencies are within the resonator cavity. You make the mirror such that you give it some coating so that the reflectivity of these modes are very low. So, they do not come back into the medium. Maybe that could be one possibility if you are able to make a mirror with that reflectivity. But then it may not always be possible, but there is one way out, one system which is called the Fabry-Perot. It is called a Fabry-Perot. It is a small element which is placed within the resonator cavity, and it does not give this, it does not give feedback to these other frequencies. They are not fed back into the resonator. Somehow they are stopped by this Fabry-Perot, and only one longitudinal mode is allowed. So, the Fabry-Perot, it is a small element. I will just give you the concept of a Fabry-Perot. So, suppose I have this as a resonator cavity, and here I place a Fabry-Perot. The Fabry-Perot are just two mirrors, polished surfaces mirrors, where the light just coming in here, it gets trapped within this, all these modes that are coming in here, they keep getting reflected in this Fabry-Perot up and down, and some interference takes place between these modes. And once that interference takes place, only one mode is allowed to pass through. The others, for everything else, there is a destructive interference. Only for that one particular mode, it is a constructive interference. Okay. So, that's how I can choose. I can choose one single longitudinal mode here. Okay. And I have achieved what I wanted. But if you just see this gain profile, this mode has created a hole in this gain profile, while this part of the gain here, those remain wasted. You have pumped in, you have given it some amount of gain, but still you have not extracted that energy. Okay. Now, suppose my aim is to get out more energy, then I would want all those modes within this gain profile, all these modes, to grow in my gain medium, or to be sustained in the gain medium, so that I get all these modes to laze, okay, and extract the gain from this gain medium. The way it is done is mode locking, mode locking or mode synchronization.